Module 10. My nervous system recently gave me an emotional roller coaster ride. Before sending me into an MRI machine for a routine shoulder scan, a technician asked if I had issues with claustrophobia, fear of enclosed spaces. No, I'm fine, I assured her with perhaps a hint of macho swagger. Moments later, as I found myself on my back, stuck deep inside a coffin-sized box and unable to move, my nervous system had a different idea. As claustrophobia overtook me, my heart began pounding, and I felt a desperate urge to escape. Just as I was about to cry for release, I suddenly felt my nervous system having a reverse calming influence. My heart rate slowed, and my body relaxed, though my arousal surged again before the 20-minute confinement ended. You did well, the technician said, unaware of my roller coaster ride. What happened inside our brains and bodies to produce such surging and subsiding emotions? Is it that the nervous system that stirs us the same nervous system that soothes us? The nervous system. What are the functions of the nervous system's main divisions, and what are the three main types of neurons? To live is to take in information from the world and the body's tissues, to make decisions and to send back information in order to the body's tissues. All this happens thanks to our body's nervous system. The brain and the spinal cord form the central nervous system, CNS, and the body's decision maker. The peripheral nervous system, PNS, is responsible for gathering information for transmitting CNS decisions to other body parts. Nerves, electrical cables form of bundles of axons link to CNS with the body's sensory receptors, muscles, and glands. The optic nerve, for example, bundles 1,000,000 axons into a single cable carrying messages each eye sends to the brain. Information travels in a nervous system through three types of neurons. Sensory neurons can carry messages from the body's tissues and sensory receptors inward to the brain and spinal cord for processing. Motor neurons carry instructions from the central nervous system out to the body's muscles and glands. Between the sensory input and motor output, information is processed in the brain internal communication system via its interneurons. Our complexity resides mostly in our interneuron system. Our nervous system has a few million sensory neurons, a few million motor neurons, and billions of interneurons. The peripheral nervous system. Our peripheral nervous system has two components, somatic and autonomic. Our somatic nervous system enables voluntary control of our skeletal muscles. As the bell signals the end of class, your somatic nervous system reports to your brain current state of your skeletal muscles and carries instructions back, triggering your body to rise from your seat. Our automatic nervous system, ANS, controls our glands and muscles of our internal organs, influencing such functions as glandular activity, heartbeat, and digestions. Like an automatic pilot, this system may consciously overridden, but usually operates on its own, autonomously. The autonomic system serves two important basic functions. The sympathetic system arouses and expends energy. If something alarms or challenges you, your sympathetic nervous system will accelerate your heartbeat, rise your blood pressure, slow your digestion, raise your blood sugar, and cool your perspiration, making you alert and ready for action. When the stress subsides, your parasympathetic nervous system will produce the opposite effect, conserving energy as it calms you by decreasing your heartbeat, lowering your blood sugar, and so forth. In everyday situations, the sympathetic and parasympathetic nervous systems work together to keep us in a steady internal state. the central nervous system. From the simplicity of neurons talking to other neurons arises in the complexity of central nervous systems, brain and spinal cord. It is the brain that enables our humanity, our thinking, feeling, and acting. Tens of billions of neurons, each communicating with thousands of other neurons, yield the ever-changing wiring diagram. With some 40 billion neurons, each connecting with roughly 10,000 other neurons, we end up with perhaps 400 trillion synapses, places where neurons meet and greet their neighbors. A grain of sand-sized speck of your brain contains some 100,000 neurons and 1 billion talking synapses. The brain neurons cluster work groups called neural networks. To understand why Stephen Kosling and Oliver Cohen have invited us to think about why cities exist. Why don't people distribute themselves more evenly across the countryside? Like people networking with people. Neurons network with nearby neurons with which they can have short, fast connections. As in the figure above, each layer cells connect with various cells in neural networks. Next layer. Learning to play the violin, speak a foreign language, solve a math problem, occurs in experience, strengthens connections. Neurons that fire together, wire together. The other part of the CNS is the spinal cord. It is a two-way information highway connecting to the peripheral nervous system in the brain. Ascending neural fibers send up sensory information, and descending fibers send back motor control information. The neural pathways governing our reflexes, our automatic responses to stimuli, illustrates the spinal cord's work. A simple spinal reflex pathway is composed of single sensory neuron and the single motor neuron. These often communicate through an interneuron. The knee-jerk response, for example, involves one such simple pathway. A headless, warm body could do it. Another such pathway enables the pain reflex. When your finger touches a flame, neural activity travels via sensory neurons to interneurons in your spinal cord. These interneurons respond by activating motor neurons leading to the muscles in your arms. Because the simple pain reflex pathway runs through the spinal cord and right back out, your hands jerk away from the candle flame before your brain receives and responds to the information that causes you to feel pain. That's why it feels as if your hand jerked away not by your choice but on its own. Information travels to and from the brain by way of spinal cord. Where the top of your spinal cord severed, you would not feel pain from your paralyzed body below, nor would you feel pleasure with your brain. Literally out of touch with your body, you would lose all sensation and voluntary movements in body regions with sensory and motor connections. To the spinal cord below is a point of injury. You would exhibit the knee jerk without feeling the tap. To produce bodily pain or pleasure, the sensory information must reach the brain. The endocrine system. So far we have focused on the body's speedy electrochemical information system. Connected with your nervous system is the second communication system. The endocrine system's glands secrete another from chemical messenger hormones, which travel through the bloodstream and affect other tissues, including the brain. When hormones act on the brain, they influence our interest in sex, food, and aggression. Some hormones are chemically identical to neurotransmitters. The endocrine system are therefore close relatives. Both produce molecules and act on receptors elsewhere. Like many relatives, they also differ. The speedy nervous system zips message from eyes to the brain to hands in fraction of a second. Endocrine messages tread along the bloodstream, taking several seconds or more to travel from the gland to the target tissue. If the nervous system's communication delivers messages with the speed of text message, the endocrine system is more like sending a letter through the mail. But slow and steady sometimes wins the race. Endocrine messages tend to outlast the effects of neural messages. That helps explain why feelings may linger beyond our awareness of what upsets us. When this happens, it takes time for us to simmer down in a moment of danger. For example, ANS orders the adrenal glands on top of the kidneys to release epinephrine and norepinephrine, also called adrenaline and noradrenaline. These hormones increase heart rate, blood pressure, and blood sugar, providing us with a surge of energy known as fight or flight response. When the emergency passes, the hormones and the feelings of excitement linger a while. The most influential endocrine gland is the pituitary gland, a pea-sized structure located in the core of the brain where it's controlled by an adjacent brain area, the hypothalamus. The pituitary releases certain hormones. One is growth, the hormone that stimulates physical development. Another, oxytocin, enables contractions as hormone that stimulates physical as associated with birthing, milk flow during nursing, and oxytocin also promotes pair bonding, group cohesion, and social trust. During a laboratory game, those given a nasal squirt of oxytocin rather than a placebo were more likely to trust strangers with their money. Pituitary secretions also influence the release of hormones by other endocrine glands. The pituitary then is sort of master gland, whose own master is the hypothalamus. For example, under the brain's influence, the pituitary triggers your sex glands to release sex hormones. These in turn influence your brain and behavior. With stress, a stressful event triggers your hypothalamus to instruct your pituitary to release a hormone that causes your adrenaline glands to flow your body with cortisol, a stress hormone that increases blood sugar. This feedback, brain, pituitary, other glands, hormones, body, and brain, reveals that the intimate connection of the nervous and endocrine system. The nervous system directs endocrine secretions, which then affect the nervous system. Conducting and coordinating this whole electrochemical orchestra is the maestro, which we call the brain.